Hi guys, welcome to Easy Math.
In this video, we are going to discuss about Unit 2, that is normal subgroup for the paper Abstract Algebra. For that, we have to discuss some basic definitions. First, we have to discuss about the definition for group. A non-empty set G together with the binary operation star is said to form a group G, star if it satisfies the following conditions: closure, associative, existence of identity and inverse. Okay. First, let us discuss what do you mean by a non-empty set. If there is at least one element in this set G, means the set G is said to be a non-empty set. Okay. Non-empty set G together with the binary operation star. Star denotes either addition or multiplication. Therefore, a non-empty set G together with this binary operation star form a group G, star if it satisfies the following four conditions. Let us discuss the four conditions briefly. Also, you have to remember, always set is denoted as the capital letter and the elements from that set is denoted as small letters. Okay. First, we have to discuss about the closure property. This property is called as closed one. That is, for all A, B belongs to G, then A star B belongs to G. That means, if we are choosing two elements from this non-empty set G, means while applying this binary operation among these two elements, you get one result, right? That value is also in that non-empty set, means the set G is said to be closed. Okay. Example, I am choosing Z, plus. This set means set of all integers, right? Set of all integers means set of all 0, plus or minus 1, plus or minus 2, etc. If I am choosing two numbers, that is 2 plus 5, I am getting answer 7. 7 is also an integer. Therefore, this belongs to set. Now I am taking Z, dot. That means set of all integers together with the binary operation usual multiplication. I am choosing the same numbers 2 and 5. While operating the multiplication among these two numbers, I am getting the answer 10. 10 is also an integer. Therefore, 10 belongs to Z. Okay. Therefore, set, plus and set, dot satisfies the closure property. Now, second one is the associative property. What is that associative property? For all A, B, C belongs to G, A star B star C is equal to A star B star C. That means you have to choose three elements from that non-empty set. While interchanging the brackets among these three elements, we are getting the same answer. Let us check with the same example. I am considering set, plus. I am choosing three numbers, that is, from the set of all integers, I am taking one negative integer also, minus 2, 4 and 10. While operating this usual addition condition, minus 2 plus 4 plus 10 is equal to, first you have to simplify the terms inside the bracket, right? Therefore, 4 plus 10 is equal to 14. Again, 14 minus 2 is 12. Again, for the right hand side, I am doing that, minus 2 plus 4 plus 10. While simplifying this bracket, I am getting minus 2 plus 4 means 2. 2 plus 10 means 12. Therefore, the LHS value and the RHS value are equal. And similarly, I am considering the same example for Z, dot, that is minus 2 into 4 into 10 is equal to 4 into 10, 40. 40 into minus 2, that is minus 80. And for the right hand side, I am taking minus 2 into 4 into 10 is equal to minus 2 into 4, that is minus 8. Minus 8 into 10, that is minus 80. Here also, the left hand side and the right hand side are equal. Therefore, this Z, plus and Z, dot satisfies the associative property. Okay. Now next we have to discuss about the third one, that is existence of identity. For all A in G, there exists an element E belongs to G such that A star E is equal to E star A is equal to A. That is, for every element A in G, there exists an element E, that is the identity element in G, which satisfies A star E is equal to E star A is equal to A. Let us discuss with one example. Now we have to take the same example z comma plus. I am taking 2. When we add 2 with the 0 only, we are getting the same number 2. Therefore, 0 acts as the additive identity. Now we are considering the example set comma dot. I am choosing 2 into 1 is equal to 2. While multiplying 2 with 1, we are getting 2, right? Therefore, 1 acts as the multiplicative identity. Okay. Therefore, the existence of identity means for all A belongs to G, there exists an element E in G such that A star E is equal to E star A is equal to A means for usual addition 0 acts as the identity element and for usual multiplication 1 acts as the multiplicative identity. Next, last one, the inverse property. For all A in G, there exists an element A inverse in G such that A star A inverse is equal to A inverse star A is equal to E. That means for every element A in G, there exists an inverse element in that same non-empty set. Whenever it satisfies the condition A star A inverse is equal to E. Consider the same example set comma plus. I am taking 2 plus minus 2 means I am getting the identity because additive identity is 0, right? Therefore, I am simplifying 2 plus minus 2 means I am getting the additive identity. Therefore, for the element 2, minus 2 is the inverse element. This is the inverse element. Okay. Similar case, I am trying for z comma dot. We know that multiplicative identity is 1. But how we get? While choosing 2 into 1 by 2 means you are getting 1. This 2 and 2 get cancelled, we are getting 1. But 1 by 2 is not in z. That means is at a all integer. This is not an integer. Therefore, z comma dot does not satisfy the inverse property. Does not satisfy the inverse property. It satisfies the first property closure, second one associative and third one existence of inverse, but z comma dot does not satisfy the inverse property. Therefore, this is not a group. Therefore, this is not a group. But z comma plus is a group because it satisfies the 4 properties: closure, associative, existence of identity and inverse. Okay, next we have to discuss about the next definition, abelian group. A group G comma star is said to be an abelian group if it satisfies the commutative property. If it satisfies the commutative property. What is the commutative property? A star B is equal to B star A. Okay. A group G comma star. A group G comma star means we know that G comma star satisfies the 4 conditions, that is closure, associative, existence of identity and the inverse property. Together with the commutative property means G comma star is an abelian group. For that we are taking the same example z comma plus means, that is I am taking 2 numbers, 2 plus 5 is equal to 7, also 5 plus 2 is equal to 7. Therefore, this satisfies the commutative property, hence z comma plus is an abelian group. Therefore, z comma plus is an abelian group. Okay. Now we discuss the next definition called the subgroup. Subgroup means a subset H of a group G is called a subgroup of G if H itself forms a group with respect to the binary operation in G. That take a group G. A subset H of these is said to be a subgroup of G if this H itself forms a group under the same operation used for the group G. That means if G comma star is a group means we are taking a subset H. While applying this binary operation star, H itself forms a group under the binary operation star. Then this H comma star is a subgroup of G. Then H comma star is a subgroup of G. Let us discuss with one example. We know that Q comma plus is a group, right? The set of all rational numbers together with the addition forms a group. If I am choosing the set of all integers, this is the subset of the set of all rational numbers. Everybody knows that set of all integers is the subset of set of all rational numbers. Then already we discussed that z comma plus is a group. Therefore, z comma plus is a group. A subset Z from the group Q itself forms a group under the same operation. Then Z comma plus is a subgroup of Q comma plus. Okay. Next, we are discussing the definition left coset and right coset. That is, let H be a subgroup of G and let A belongs to G, then the set AH is equal to set of all AH such that H in H is called the left coset of H defined by A in G. Similarly, the right coset is defined as HA is equal to set of all HA such that H in H is called the right coset of H defined by A in G. First, you have to choose H is a subgroup of G. Okay. Then you have to take one element A from the group G. Then the set AH is defined as set of all AH. That means this H element is from the subgroup and A is from the group G. Then the set of all elements AH is such that H in H is called the left coset of H, which is defined by A in G. Similarly, the right coset is defined as HA is equal to set of all HA. This H is an element from the subgroup H and the element A is from the group G. Is called the right coset of H defined by A in G. Simply you have to remember that for the left coset A lies in the left side and for the right coset A lies in the right side. You have to remember the element lies in the left side means it is left coset and the element lies in the right side means that is right coset. Okay. Next, the definition used in the unit 2 topic, that is normal subgroup. A subgroup H of G is called a normal subgroup of G if AH is equal to HA for all A in G. That is, a subgroup H of G is said to be a normal subgroup if the left coset and right cosets are equal. If the left cosets and right cosets are equal means subgroup H is called a normal subgroup. Okay.
Thank you for watching. Don't forget to like, share and subscribe. Bye guys.